Thank you for coming back. And thank you for asking lots of questions in the first hour. I hope you still have some left for the second hour because those really helped. So I want to talk about unconditional lower bounds for MCSP now. And I mean mostly circuit lower bounds. So just to remind you that minimum circuit size problem is this problem of deciding if a given truth table of a Boolean function has a circuit size complexity at most some parameter S. And we really would like to understand how difficult it is to solve MCSP. Maybe it's possible to do it in polynomial time, maybe in polynomial time on average. So we don't have any unconditional results for the general problem. I think the best we can say for the general MCSP problem is this conditional hardness result that says that if you have average case complexity, if there exist one-way functions, then definitely MCSP cannot be done in polynomial time. And this is a result due to Razvarov and Rudich, essentially. And you know the proof of this, essentially, because MCSP is a killer of generators. And from one-way functions, you can get generators, and then you can kill them with MCSP. So if MCSP lives, then no one-way functions can. So that's basically the argument. So it's an average case assumption that implies the hardness of MCSP. In the realm of conditional hardness results, our go-to would be to show it's NP hard to solve something. So that would be saying, like, if P is different from NP, then there's no polynomial time algorithm for MCSP. And this is a big open question to get the NP hardness of MCSP, but we're that close, or as Rahul explained in his introduction. So maybe one day, but those results would be conditional. So what about unconditional lower bounds? And I will talk about unconditional circuit lower bounds for MCSP. So this is a non-uniform model of computation. And of course, I'm not going to show you general circuit lower bounds, I wish, but we don't have those for any problem, basically, let alone for MCSP. But if you allow me to talk about smaller circuit classes like AC0, constant depth, and the like, then we can get some results for MCSP. In particular, if you talk about constant depth, also known as AC0 circuits, then you have lower bounds for MCSP to be of the form 2 to the n to the 1 over depth. I'm ignoring some minor constants in there, so please forgive me for not burdening the notation, but it's basically the state of the art with appropriate constants plugged in. For De Morgan formulas, it's a cubic lower bound. Here, capital N is the size parameter, the input size parameter to the function that tries to compute MCSP. So it's 2 to the little n normally. And for AC0 mod P circuits that we talked about earlier, depth D with mod P gates for any prime P, the lower bound is also exponential. It's 2 to the n to the 1 over 2D, roughly. And as I said, these bounds match the best known bounds for explicit functions in NP. And here they prove they can be proved for MCSP. Which is a bit surprising because MCSP seems like a very complicated function. And normally to prove circuit lower bounds for some function, you pick a function which is not too hard, that has some nice structure that you can exploit to get the lower bounds going. And here we have very structureless, or as far as we understand, very structureless problem like MCSP, and it's not clear how to apply the classical methods of proving circuit lower bounds to that unstructured problem. I'm not going to go into details, but usually like lower bounds for the models that I define for constant depth or De Morgan formulas, you use combinatorial techniques like famous ones like method of random restrictions or polynomial approximation. And I'm not going to define exactly what those are, but this is the classic stuff. And unfortunately, it's not clear how to apply those methods to this structureless problem MCSP. Like random restrictions work really well for parity function because parity is like immune to random restrictions. But what happens when you restrict MCSP? Who knows? It's not clear how to analyze that. So we'll be using something different to prove lower bounds for MCSP. Now, in the previous hour, I talked about the power of MCSP as the ultimate killer of pseudorandom generators. Now we're going to use that power against MCSP to show that MCSP cannot be computed by small class circuit, because we have pseudorandom generators against small classes of circuits. Okay, so the general framework to prove lower bounds for MCSP via PRG is to set up the game where you have a pseudorandom generator G, which is a good generator for the class of circuits, script C. And then you argue that your MCSP will be able to break this generator. So this generator does not fool MCSP, which implies that MCSP cannot be from that class C for which the generator is supposed to work. All right, and now you just choose appropriate C here, appropriate G there, and that will give you that MCSP is not in that class. And then the parameters will just tell you how good a lower bound you get here from how good a generator you have for how big circuits, how big of a circuit can it fool and from what class. So that's a general framework. And as we observed before the break, MCSP is really good at breaking local pseudorandom generators. So here I'll may confuse you by saying, by giving the definition of local again, but it's more like a property of local. Basically, as I said, generator being local means that it can be broken by MCSP. That's all I need here. So the generator is something which stretches a seed into the output of the generator of appropriate length. Here I'm going to be thinking of the outputs of the generator as truth tables of Boolean functions. So it's the size of the output is like capital N, which is 2 little n, the same convention as before. And I say that this generator is local is if for every seed to the generator, the output of the generator viewed as a truth table has sufficiently less than the maximum circuit complexity. And the maximum circuit complexity is something like 2 to the n over n by classical work on circuit complexity. However, for a uniformly random truth table for a random function, the complexity of random function, circuit complexity of random function, is strictly bigger than 2 to the n over n, again, by the classical counting arguments. So if I set my threshold for the MCSP algorithm to be this close to maximum, capital N over little n, then this MCSP will break any local generator whose output has relatively small circuit complexity. So this is the framework. This is the takeaway, that MCSP breaks every local G, and we just make the size parameter to be capital N over n, close to the maximum. So just to remind you, what does it mean to be PRG? PRG for a generator G is a pseudorandom generator for a circuit class C if no circuit from the class breaks it, which, repeating myself, means that if I have a local PRG for some class of circuits, then MCSP is not in that same class of circuits. And that's what we're trying to use. And some things are very easy, and some things don't require much work. You can just take things off the shelf, but some things you need to work. It's harder to use this approach to get like strong enough lower bounds. Local PRGs are known for a bunch of models of circuits. The classical one is for AC0, the original work by Nissan, who gave a pseudorandom generator, Nissan-Wigderson style, based on the parity function as a hard function. And therefore, immediately you get that MCSP cannot be in AC0 because you have AC0 secure pseudorandom generator. The size parameter, you have to be very careful, like you maybe fine-tune some parameters, and you can fine-tune them enough that the circuit lower bound you get will be essentially the optimal one that we know for general functions in class NP. Now, we also have a generator for to fool De Morgan formulas of cubic size. This is from the result by Impaglazzo, Mecca, and Zuckerman, and with some improvements by Chiragci, myself, Lou, and Mirisotis. And before this work, like you had a generator for De Morgan formulas of about quadratic size, and these people managed to push this to larger circuit complexity and get a generator that fools bigger things. And it's good for us because once you have the generator that fools cubic formulas, then you show that MCSP is not in cubic size De Morgan formulas. So good work there implies good lower bound for MCSP with respect to De Morgan formulas. So what about AC0 mod P circuits that we defined before the break? So these are constant depth circuits with modular gates, mod P gates for prime P. Unfortunately, we don't have good PRGs for that class of circuits. And that's in itself a very important problem in pseudorandomness. But we do have some PRGs. And this is coming from the work of Pfefferman, Chaltiel, Humans, and Viola. In the context of hybrid arguments and the limitations of hybrid arguments, they gave this construction of a PRG with not very good stretch, but still some non-trivial stretch. So what did they show? They've shown that you have a PRG that fools AC0 mod P circuits of weakly exponential size. So think of M as the input size of the circuit that you're trying to fool, so the number of inputs. So the output of the generator are passed to a circuit that takes, the output of the generator is like some function of the input size. So the generator maps M truly random bits to M plus M over M to the epsilon pseudorandom bits. So normally, the generators that we like have at least polynomial stretch. So you go like from M to M square or M cube, even better like exponential. For pseudorandomness, exponential is even better. But this generator just only does additive stretch here. The seed length plus a little bit more. Okay. And there's a good reason why we only have this kind of generator. And the reason basically comes down to no good circuit lower bounds are really known for AC0 mod P good enough to construct a generator from. I mean, they are weakly exponential, but they're not good enough to get a good generator like any Sandwich wants. Intuitively, because majority is not computable in AC0. So this generator from this paper by Pfefferman et al. Is not local in the sense that it's not breakable as far as we know. Actually, may get to talk about this later. It may be broken by MCSP, but we just don't know if it is. Okay. But as far as we know, this generator is not local in that we don't know if MCSP breaks it. So we cannot just take this generator and be done by saying, okay, MCSP breaks, therefore MCSP has this weakly exponential circuit size complexity. So we need to do some work. Okay. Yes.
Maybe this is naive, but is it possible? Like, is a converse possible? Like, could it be that if MCSP is not in the class, then PRGs don't imply PRGs for the class? Or like local PRGs, I guess.
I'm not sure. It's a good question. I'm not sure.
That's possible. Possible. Yeah, it's a good question.
It's a topic for one of the seminars in the semester. Yeah. Okay. So if you have something which is not strong enough for the problem that you're trying to solve, what do? You change the problem you're trying to solve. Okay. So that's workaround number one here that I want to talk about. And so instead of saying, oh, we're going to use MCSP to break a generator and therefore MCSP will have high circuit complexity, we're going to say, hey, MCSP does not seem to be strong enough. We call up its Kolmogorov relative, MK capital TP, and that thing is strong enough to handle these generators, and we'll be able to break it. And therefore, we get that MKTP requires AC0 mod P circuits of size to the end of epsilon. Okay. So that's number one. I'll talk about this in a moment, but don't worry, I'll talk about how to get MCSP lower bound as well. But the result will be a bit more complicated to state, so please bear with me. Instead of saying simple to understand thing like MCSP breaks a generator, we have to say the following. Certain restriction of an MCSP will break certain version of that generator. Okay, so we'll find a version of the generator to break, and we'll also argue that there's some restriction of an MCSP circuit that can be used to break it. The size of the restriction of MCSP circuit will be of the same size as the original one. And this version of a generator will still be a generator, so it will fool AC0 mod P with weakly exponential size. So that would still imply that there's some restriction of MCSP must be large circuit complexity, and therefore the original MCSP must also have large circuit complexity.
What is a restriction?
I will talk about that a bit later, but think about it like somebody gives you a circuit for MCSP and you say, thank you so much, but I'm going to modify it a little bit. And the modification will basically be that for some positions, you say, you know what, I'm going to hardwire zeros in those positions, and we'll leave them like that. That will be the restriction. So we'll use the same circuit, but some inputs you're going to ignore by plugging in zeros in there.
But you said before that these methods don't work here. Isn't that what you said? That's the usual ways we prove lower bounds.
The usual way to prove lower bounds would be to say that if you have no, so usually you say that, okay, give me a function that you want to prove a lower bound for, and if function has nice structure, like then you say, oh, let's hit it with a random restriction. It will simplify too much, and I can prove it to you. And that's impossible because you cannot simplify too much. And that will give you a lower bound. And usually to argue that something simplifies enough under random restriction, you need to understand that function well enough to really talk about it. Like, you take your parity function, or that's very easy to understand. Maybe majority with some work you can understand, but MCSP, what happens when you hit it with a random restriction? What I'm talking is not quite a random restriction and not a restriction in the usual sense. And I'm not going to use it to actually say that the function simplifies. So it will be a restriction of a circuit, but don't think about this as a random restriction as a method to prove lower bounds. It's not.
And at the end, you'll get a lower bound for MCSP.
Yes, yes. For the normal one. Yeah. That will be honest. Yeah.
So I think regarding that local pitting effect, right? And if that's the case, then local pitting effect also implies zero error everything highest of for MCSP. Yeah, so
So let me talk about the easier point, item 1. And I will remind you this notion of KT complexity. So personally, I think of MCSP as the complexity, like circuit complexity being an object from the world of circuit complexity, because it talks about like what is the size of the computational model that you need to compute a function. Now, in the Kolmogorov world, things are a little bit different, although very similar, in that you give me a description and you also take into account the time that it takes to recover the object from the description. I'm talking about time-bounded Kolmogorov complexity now, as we usually do in complexity theory. So unbounded Kolmogorov complexity, you can take arbitrary number of steps, but for the time-bounded, you need to take into account the number of steps, not just the description size. For the circuit complexity, for MCSP, you just say the circuit size, and you don't really explicitly mention how long it takes to recover the string, the truth table from the circuit. Yes? Normally, it would take maybe quadratic time in the size of the circuit, because we work with the Turing machine model. So you have some polynomial overhead in the reconstruction, which MCSP does not reflect. Okay? MCSP just talks about the description size, the circuit size, doesn't talk about the time it takes to compute the circuit on all the inputs. Kolmogorov complexity, KT, is like the Kolmogorov version of circuit complexity that is fair in that sense. It explicitly talks about the time it needs to recover a particular bit in the string X. Okay. So this is like really being from the Kolmogorov world, but it's a very close relative of MCSP. But it's more honest in that it takes time into account. Okay, so let me say it more formally just in case. So given a string of length n, KT complexity will be the sum of two things, a program of size D, size length of D, program D, description D, and the time in unary, number of steps, such that some universal Turing machine with random access to its input tape on an index I can produce the ith bit of the string X in time t. So like any input position you want, you can recover in at most t steps, given your random access to the description D and given the index of the position explicitly. So this notion of Kolmogorov complexity is sufficient for us to argue that we can break this poor stretch FSUV PRG for AC0 mod P. For every seed Z to the generator G, the Kolmogorov complexity, Kolmogorov T complexity, I think Rahul talked Allender's complexity, so maybe it should be like A. But anyway, so Kolmogorov capital T complexity of the output of the generator will be at most the size of the seed plus something small. And I'll explain why. Whereas, and remember, the output of the generator is going to be m plus m over m to the epsilon. So it's m plus almost m, which is very large compared to m plus m to the epsilon, which is much smaller. So for a random string X of length m plus m over m to the epsilon, the KT complexity will be about m plus m over m to the epsilon. Like almost every string is incompressible. And as Rahul mentioned, this is true for any model of Kolmogorov complexity that you can use. Because it all follows by counting arguments. Now why? So the second point is easy, it's by counting. Why is the first point? Why KT is a killer of this kind of generator, FSUV generator? Well, you need to look at what the generator does. And the generator that FSUV use is basically a direct product generator for the function parity. Let's think about AC0 mod 3 circuits here, for which you can use parity to fool them, because AC0 mod 3 circuits are not smart enough to compute parity. What you do is you take the input, which you can think of, input of length m, which you think of as a tuple of k strings of size m over k, and think of k as being m over m to the epsilon, which works out for every string in the tuple to be of length like m to the epsilon. So if you do the math, the size of the input here is going to be exactly m. The size of the output, or the output will be the seed itself. So you take your x1 through xk and output them, plus you evaluate your parity function on each one of them and append them at the end. So basically direct product construction for the parity function, but you include the inputs as well. Like incidentally, Nissan-Wigderson generator is normally defined where you just output the values of the functions on the inputs, which are like partitioned using the clever design construction. And you normally don't bother including the seed, but you could. Okay. So one way to say this is like, it's like Nissan-Wigderson generator without designs, using parity as a hard function. Okay, like design-free Nissan-Wigderson. It's a strange thing to say, but anyway, that's what it is.
Zero, yeah.
What?
There's just no intersection between the pairs of sets.
That's right. That's right.
Simple design.
Yeah. It's very simple design. It's a very trivial kind of design, yeah, where you don't care about compressing. And this is actually a very interesting point. Maybe I'll remember to come back to this later. The difference between Nissan-Wigderson generator with actual design and like trivial design or no design Nissan-Wigderson, which is this, and like how they play in terms of context of learning, for example. All right. So now that we understand the structure of this generator, let's see what is the KT complexity of its output. Well, if you want to compute this string, you definitely need to know the inputs x1 through xk. So that will be part of the Kolmogorov description, the inputs. This is of size m, as you remember. But then the parity of each xi you can compute yourself. And it takes small time because parity is an easy function. And that will give you plus the time to compute the parity. So KT tells you, okay, I want to know the bit in this location. You say, oh, that's very easy. It's like a truth table lookup for appropriate input. Something complicated. I want to know the bit in this location. Okay, I need to figure out which string xi corresponds to this position. And then I need to do the hard work of computing the parity of those bits in that string. But that's time of the parity, which is essentially linear in the size of the input of the parity. And the parity was on m to the epsilon size input, so that's m to the epsilon for you. That's it. So that is the proof. Sketch why KT will kill this generator of FSUD. As a consequence, KT MKTP function has high AC0 mod P circuit complexity. So that was easy. And I should mention that this is basically was done by Eric Allender and co-authors, and then also by Rahul and Shuichi, I believe. So, I mean, they did a little bit more. Huh?
I don't think I was involved with that.
Well, you have a lower bound for MKTP against AC0 mod P, using a different way of proving things. But the lower bound for MKTP was coming from the work of Eric, and then some improvements from Rahul and Shuichi. And Rahul and Shuichi basically were using this framework. All right, so as I promised you, I promised you to show that MCSP itself, not its Kolmogorov relative MKTP, also requires AC0 mod P circuits of high size. As Eric can tell you in a much better way, there are a few results in complexity of Kolmogorov problems which are much easier to prove from MKTP than they are for MCSP. Okay, and this is one example where for MKTP, I've shown you the complete proof of the lower bound for MKTP, assuming the hardness of this, assuming the security of this PRG from this paper by FSUD. But for MCSP, you need to work much, much harder because MCSP does not seem to kill those generators, even though I suspect it does. We just don't know how to prove it. I'm reminding myself to talk about that later. So what do we prove? So in a paper with Golovnyov, Rahul, Ilango, Impaglazzo, myself, Kolokolova, and Avish Shaital, we show the following. And this is not the way we stated in the paper, but I think it's the same thing. So I hope to convince you. Avishai will check and will let us know. So this is how I'm thinking about the result from that paper. Let's fix the AC0 mod P circuit size complexity of the function MCSP. So let's denote by S of capital N the circuit complexity, like the size of the best circuit for MCSP, where the circuit is of this type, AC0 mod P circuit. Okay. Then for every large enough input length, so the result is asymptotic as normal. So for large enough input sizes, there exists a PRG G, which is a good PRG against AC0 mod P circuits of large size. And there also exists an AC0 mod P circuit, which is of size at most this S of n. Okay, and this is the restriction of the MCSP circuit that I was talking about, which breaks the generator G. So this is like more detailed way of saying that there exists a version of the generator and there exists a smaller circuit which breaks this generator. And the smaller circuit comes from this assumed circuit for MCSP of AC0 mod P type. Does it look right? Maybe? Maybe.
You're assuming MCSP has a circuit that has, well, this S of it has to be at least 2.
Oh yeah, exactly. Yes. So I didn't say, thank you, Ryan. I didn't say this explicitly, but if you like put these things together, then what's the conclusion? Well, because this circuit C breaks the generator, the complexity of the circuit C must be at least 2 to the n to the epsilon because the generator is secure for those guys. And the circuit C is of size at most S, which means that S of n must be at least 2 to the n to the epsilon. And S of n was the complexity parameter, complexity size for the MCSP. So the complexity of MCSP must be at least 2 to the n to the epsilon. Ida, you have a question? Oh, yeah, please.
Are you saying that unconditional PRG against the fundamental effect in the
Yeah.
Oh, I see.
Yeah, like this PRG-G is going to be like non-uniform PRG. And the circuit C that breaks it is also going to be like a non-uniform version of the non-uniform circuit given for MCSP. So it will be like some kind of non-uniformity added to the things that you start with to get a version of a PRG and a version of the circuit to break it. So it's like inherently non-uniform construction. That's what makes it interesting. So you see I'm nodding now, so it comes back. Yeah.
It's a different presentation, so
It's very different, yeah. I wanted to surprise you. I wish I was one of the authors on that paper, which was, by the way, written at Simons during earlier program on Simons. And like, so yeah, Simons is a very good place for writing papers. So, okay, let me give you a little bit more details. I'm not going to do the whole thing, even though it's kind of interesting, but just want to whet your appetite. And maybe if you haven't read the paper, you can do the paper, even though the presentation is different. But here, the FSUV generator that we're going to use is a so-called biased coin generator, which I'm going to define. So the output of the generator, and sorry, I'm switching the notation here a little bit to help myself. So the output of the generator will be of size capital N. Think of capital N as like the truth table of a Boolean function that we usually do. And each of those capital N bits will be independent, a random variable set to 1 with some probability half minus gamma and to 0 otherwise. So it's a bunch of biased coin flips with slight bias. Gamma will be some function of the size n. For us, it will be roughly 1 over square root of n. It's almost biased. So why is this a generator? Maybe I should say why this is a generator. So if I have like n bits, and each bit is of this bias, half minus gamma, then intuitively, because it's not a perfectly biased thing, it's compressible, all right? Like think of gamma to be 1/2, then it's an extreme case, of course, but like then all bits are the same, then I can definitely compress it really well. If gamma is like some constant, then you still can compress it quite a bit because, you know, there are not so many sets with a few elements from the universe of a given size. Unfortunately, to use this generator to break AC0 mod P, AC0 mod P is not that silly. So it can distinguish some kind of bias a little bit. So you need to have a bias so that you very close to 1/2 to make it useful. Okay, so gamma should be kind of very small, and when gamma is very small, your bias coin is almost unbiased coin with just a little bit in the direction of being biased. And when you think about compressing this, you'll get a little bit of savings, but not too much. Okay, so why am I talking about the compressing of this thing? So I'm saying that this string can be compressed into something which will be of length roughly n times the entropy of 1/2 minus gamma, the entropy of the bias. Yeah. And this compression and decompression are known to be computed efficiently. And this compression is known that does optimal compression, like what I said, which is remarkable, I find. And it's very simple. And so what is this? This is roughly like the binary entropy function of 1/2 minus gamma is about 1 minus gamma square. So this is roughly n1 minus, 1 minus gamma square. Gamma is like very close to 1/√of n. It's going to be slightly less than that, because if it was that, then this would be 1 minus 1. I mean, this would be, yeah, like basically n, right? So you would have no savings whatsoever. If you make it slightly smaller than 1/√of n, then you get a little bit of compression going on, but not that much. Okay, and think of gamma is like 1/n to the epsilon. Then you get some kind of compression here. You go from n minus n/n to the epsilon to n. Okay, I was talking about this generator before, and now I'm talking about compression. What's the connection? Well, just think about this in the reverse direction. That will be your generator. All right. So because the compression is optimal and efficiently computable in both directions, if you give me a uniformly random string of that size, I can compute the string of slightly bigger size that will be slightly biased. Make sense? And this is one of the versions of FSUV generators that they mention in their paper, but they don't spend too much on it. They just mention it in passing. But this version of the generator happens to be exactly what we use in this lower bound, even though the presentation is not that, but can be made to use that generator. So that's the bias coin generator for you. And what is the circuit C? The circuit C, as I mentioned in answering Tal's question, is going to be your MCSP function, where the inputs to the MCSP function are going to be fixed non-uniformly in some places. Okay, you're going to fix two things. You're going to fix the size parameter S star here. It will be something special that we have no idea what it is, but it can be found by some kind of averaging argument and non-uniformly fixed. And in your truth table that MCSP usually expects to get, you'll have the whole truth table, except that with some non-uniformly chosen positions will be fixed to zeros. You just override. So yeah, there's some x2 that comes in as an input, but you're going to ignore what x2 is and just think of it as 0 always. So that will be the restriction of your MCSP. Yeah. Both of these choices are very non-uniform. We have no idea how to compute them uniformly. So they just appear by some kind of averaging arguments. They exist. Yeah.
Why is the PRG not?
Because I need to know gamma.
Oh.
And I don't quite know gamma. I know it's going to be of this order of magnitude, but what the constant is, I'm not sure. So there will be some particular bias, roughly of that order of magnitude, that will be good for me. But which one, I'm not sure. But it will exist.
Thank you.
You're welcome. That's very good. Thank you for asking. That's a good question. Not sure, but that would not be as cool as this. Right, Ryan?
I like yes.
All right, forget that. So, yeah, I don't know. Because as I said, the presentation now is different from what we originally did. So I haven't thought in the context of generators what you can do once you have this idea. So maybe. One of the corollaries of this, I'm going to talk about some details of this construction in a moment. I have time for that. But I find it's an interesting corollary. So Rahul talks about the difficulty of proving NP hardness of MCSP. And NP hardness of MCSP is like showing that SAT can be solved if you know how to solve MCSP. And the reduction can be any kind of efficient algorithm that may use MCSP any way it likes. So it could be adaptive, crazy, asking MCSP question a bunch of times on related inputs, whatever. And there's been a lot of work, and maybe Rahul Lango is going to talk about some of that work tomorrow in the context of disproving that certain reductions to SAT, MCSP to SAT, SAT to MCSP do not work if you restrict your reductions enough. On the positive side, you can prove some reductions from non-trivial things to MCSP, which follow from this work combined with an earlier work of Oliveira and Santana, which in turn is based on CIKK that I talked in the previous hour. So combining all of those ideas, you can show that any function in NC1, so anything which is computable by small polynomial size De Morgan formulas, can be computed by a constant depth circuit, AC0 circuit, which has oracle gates for MCSP. And I think it's going to be very adaptive. So the reduction is very simple, AC0. It's efficient, polynomial size, but super adaptive and also non-uniform because of the reasons that I just mentioned earlier, like to know the bias, to know the size parameter S star, and which positions to fix with zeros. All of those things will come into this non-uniformity of this AC0 reduction. So it's non-uniform AC0 reduction, highly adaptive probably. So that tells you that you can use MCSP for solving some non-trivial problems like anything in NC1, for example, but you have to be really clever to use MCSP, and you have to be probably using it adaptive if you want to get some mileage from it, which may also explain why it's so darn difficult to come up with such reductions, because in NP completeness world, we used to relatively simple reductions.
Can you make it a uniform probabilistic reduction?
Possible. I haven't thought about this. I have to really go through all the non-uniform parts in this construction, and they by averaging hybrid arguments. So yeah, you can have some non-trivial but kind of low probability. So I guess probabilistic will be maybe with probability 1 over square root of n or something like that. I'm not sure. We work with low error regime. So yeah, so before I do the summary, let me just give you some more details. And this is the original presentation of this result from the paper I mentioned with Avishai and others, where we showed that you can use MCSP or some restriction of MCSP to break this bias coin generator. And that, what it means is you can distinguish between a sequence of bits which are epsilon biased, so each bit with probability almost half, versus uniformly random string, which is unbiased string. And the reason why breaking such a generator is good for proving AC0 mod P lower bounds is that there was a nice result by Chaltier and Viola, who showed that any distinguisher for these two cases, uniform versus slightly biased distribution, can be used to get a circuit to compute majority. And because majority is a hard function for AC0 mod P circuits, your distinguisher probably cannot have small AC0 mod P complexity, if it can kill these things. Okay, now to prove that MCSP has non-trivial AC0 mod complexity. You just need to show that MCSP distinguishes these two cases. And we're almost there. The actual thing that we use is that improvement of the Schottky-alveolar result due to Limaya and others, who shows more precisely the parameters. Like if I have an algorithm that distinguishes slightly biased from uniform, where the bias is epsilon, then the distinguisher which does this distinguishing task gets circuit complexity of AC0 mod P type of, and there's a formula. So some version of MCSP distinguishes epsilon bias from uniform, but that's not quite true. And so let me explain to you, let me try to give you an idea like what the obvious approach would be and why it doesn't work, or at least we don't know if it works, and why we had to do this other crazy things. Now, as I mentioned before, for truly random strings, MCSP of the truth table will have, like, we'll say no with this size threshold, meaning that almost all random strings have very high circuit complexity. Now, what about epsilon biased truth table? So typically, if you flip a coin with probability 1 being 1/2 minus epsilon, you expect to have 1/2 minus epsilon once, fraction once in your string. And so, yeah, so this set with so few ones, relatively speaking, will come from a set of all sets with so many ones, which is n choose 1/2 minus epsilon times n, which works out to be exponential with this binary entropy function times n in the exponent. I already used that fact when I talked about compressibility of this bias sequence. So yeah, so this basically says that this string with few ones is compressible to about this size that I mentioned before. So 1/2 minus epsilon bias gives you 1 minus epsilon squared times n bit size. So this string can be specified using this many bits, 1 minus epsilon squared times n bits. And for MKTP, that was enough. For MCSP, we need to argue that actually this string of biased bits can be computed by a circuit of size 1 minus epsilon squared times the maximum possible size, which is like 2 to the n over n over little n. And like, you know that the like normal description is of this size. Why wouldn't the circuit description be like what you expect it to be? Like normally, random strings have bit complexity, the length of the string, but the circuit is like that thing divided by the log of the length of the string. Okay, that's like usual bounds due to Lupanov and others. So Lupanov, in fact, showed that, you know, if you have unbiased random string, then its complexity will be at most 2 to the n over n, or capital N over little n in my notation here. And for biased ones, yeah, it's almost like this. It's almost like that. So he showed that a typical epsilon biased truth table will have circuit size 1 minus epsilon squared times 2 to the n over n. So far, so good. And I wish he stopped there, but then he had to add some error terms. And the error term is like this n over little n squared. Why is it bad? Well, let's open the brackets here. So this is like n over n minus epsilon squared, n over little n. These are my savings from the bias thing. And then plus the error term. And this error term is gonna eat up all my savings because my epsilon will have to be at least like 1 over little n. Actually, it will be like 1 over poly little n. So like all my savings evaporated because of the error term in Lupanov's result. And I'm just wondering if he could work a bit harder and gotten a better result, then we would have got a like very simple proof of why MCSP has high circuit complexity relative to AC0 mod P circuits. But we don't know that. So it may be possible. So it may be possible that this can be improved. Will probably require a lot of work. And I'm not sure if people really tried. I'm not sure if people are really motivated to work on that.
such a class term?
Yeah. Like, yeah, you have like very good approximations of the circuit complexity of random functions, both upper and lower bounds. And it's like, it's good here. And then the second order error terms, we're not 100% sure they typed. And this is one of those second order error terms which we don't know it's typed or not. And so the actual proof that we have to do, we start with the Lupano result for constant bias epsilon, for which the savings is really good, because when epsilon is constant, some like say 1/10, this savings is like constant fraction n/n, and the error term is then negligible, n/n². So for constant epsilon, Lupano's result is great. So we use that, and then we kind of do the hybrid argument to go to say, okay, for constant bias, we have small circuit. For bias close to 1/2, we're not sure, but let's do some kind of hybrid argument and argue that there will be a good place where you have some nice gap between like size of the circuit for this bias versus the size of the circuit for the slightly bigger bias. I don't want to go into more detail than that. And then you also use some kind of Chernoff-like concentration results for circuit size of random functions to finish the argument and argue that there will be a good threshold to choose that comes from the hybrid argument, such that there's a good enough gap between small bias and slightly bigger bias. And then you do like rescaling to get from this to biased versus unbiased, which is random versus slightly biased. And when you do the rescaling, some things will have to be fixed to zeros in the input to the MCSP function. And where they do get fixed, you don't know, because it depends on the biases that come from the hybrid argument. And this is the non-uniform part of the construction. But if you do all those things, then you get the result that I mentioned before, that you can break a bias point PRG using some restriction of MCSP circuit that we have, using some non-uniform choices. So summarizing what I talked about. So the takeaway message from my tutorial here was to say that MCSP breaks local generators, and it's really good for learning if you have access to MCSP heuristics, average case MCSP algorithms. And it's also good for proving lower bounds against MCSP with respect to weak classes where you have PRGs. And again, Shuichi is going to talk about more applications of the generators. Thanks.
Before you ask some questions, just a quick announcement about the talk tomorrow. So Shuichi is unwell, so you won't be able to speak tomorrow morning, but Eric and Igor have volunteered to speak, so we have them speaking instead. And now more questions.
That we do not know to code for MCSP. Like threshold of maturity. That is sort of taking care of this paper. Because they reduce from this projection.
Could you repeat the question and the answer? Could you repeat the question and Rahul's answer?
Oh, I was asking, are there any example function which we know lower bound for, but we do not know the same thing for the MCSP problem?
What about PRGs, the guy right next to you? What about him?
I find this purchase. The 3.1.
There's one example I'm trying to remember. We could do a depth to threshold circuit lower bound for MKTP that's still open for MCSP.
Yeah, but does the size have straight off on TC0?
It's pairing. Like it's fine. Roy and my people, they have something.
They have a PRG.
So let's thank Valentine again.